and other invitees to this online talk. As you know, we have been conducting these talks on various topics since last year, last October, for the benefit of our students, teachers, and the general public. So our idea is to at least inform the way members about developments in various fields in a very comfortable setting. They don't have to travel outside their home. So at least they can learn few things apart from their own topics of their main interest. That is the idea. So we have been doing this, and we are very thankful to so many faculty members from institutes, universities, and colleges who have volunteered to share their knowledge on various topics. And we have also conducted these talks in Kannada also. So our idea, of course, one of the objectives of KPA is to introduce Kannada at the higher education level. So it is essential, not because our students need it, for proper understanding and proper communication. Even the teachers find it very difficult. Let us be honest. So we have to make an attempt in introducing our own languages at all levels, and even NEP, UGC, and even this Council of Engineering Education. They are recommending. So do that. So we are doing that. So today we have a very distinguished speaker, SP Ananda, who has served as a scientist at MCF Hassan, and he will go to tell us about the MCF facility, MCF at Hassan and its activities. So before I request him to talk about it, so I just want to introduce him to this audience. Of course, you all know about him already. He obtained his BSc from Mysore University in 1984, MSc from Bangalore University with solid state specialization, and studied at Malnad College of Engineering, Hassan, for postgraduate diploma in computer programming. And then he joined the Malnad Engineering College as a lecturer, starting a career. Later, for a few months, he worked as a PhD student at ISRO Bangalore in the physics department. He joined MCF Hassan in the year 1986. He has worked in spacecraft operation group, worked as spacecraft controller and shift manager for operations and control of geostationary satellites. He was deputed to so many countries, which Italy, and so many places, to support INSAT 2D missions in the year 1997. He has worked in computer systems and simulation group, held different functional positions as head of the computer software, and retired as group director SPROC systems in January 2024. He was instrumental in establishing optical telescopes, laser ranging, and optical communications at Mount Abu, Rajasthan, and also at a place in Ponamudi in Kerala for monitoring Indian space assets. He was involved in 50 plus satellites pre-launch activities and launch and orbit raising activities from 1986 to 2024, very crucial activities. He had delivered several talks at several institutions, especially at schools, colleges, and universities, and very much interested in popularizing science education and computer science at various levels. He has worked as a guest faculty at Hemagangotri PG Center at Hassan, where he taught optical fiber communication to MSc students. And he was a leader of the task team to establish 3 computer labs at Government Science College Hassan under CSR program. He has published several technical papers and presented them at conferences and guided several BE students for their projects. We are very thankful to Ananda, HD Ananda, for agreeing to give a talk about MCF and its activities. Over to Ananda, sir.
Thank you, sir, for a nice introduction. Before I proceed further, so when I say MCF Master Control Facility, initially when it started, there was only one center at Hassan. In the later stages, to address the disaster management in case some problem happens to Hassan, whole national vital assets will get disturbed. So with the keeping into account in mind disaster management and natural calamity, one more backup center at the Master Control Facility at Bhopal was established in 2007. So we have two centers, Master Control Facility Hassan and Master Control Facility at Bhopal. Some satellites are controlled from Bhopal. Majority of the satellites are controlled from Hassan. So we have the facility in case of any problem in Hassan.
Excuse me, can you speak louder, a little bit louder? So voice is low. Please speak a little louder, okay, if you don't mind.
ಏನಾದರೂ ಕಡಿಮೆ ಇದೆಯಾ ನೋಡಿ.
ಸ್ವಲ್ಪ ಹತ್ರ ಬನ್ನಿ. Come closer to your microphone.
ಓಕೆನಾ ಸರ್ ಈಗ? ನೋ? ಈಗ ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ಸರ್? ಓಕೆ. ಹಲೋ.
Better.
ಸರ್ ಅಷ್ಟೊಂದು ಚೆನ್ನಾಗಿ ಕೇಳಿಸ್ತಾ ಇಲ್ಲ.
Better. Come closer to this microphone.
ಮೈಕ್ರೋ ನಂದು ಆಡಿಯೋ ಏನೋ ಕಡಿಮೆ ಇಟ್ಟಿದ್ದೀನ ನೋಡೋಕೆ.
Okay, make it so amplification ಜಾಸ್ತಿ ಮಾಡಿ. Okay, please continue.
Yeah. Before coming here, I just informed that the Master Control Facility 2 centers have been established now. Now the first question is the need of establishing Master Control Facility. So in the year before in the 1970s, there was one experiment called SITE experiment was done. It's called Satellite Instruction Television Experiment to look at the feasibility for a satellite-based communication. So it was actually a combination. It was an application program to find out the sizing of the satellite. So after the experimental study of SITE experiment, where they in each state they established one receiving station using one of the NASA satellites and came out with the sizing of the satellite. So later, in the INSAT study is jointly carried out by ISRO and MIT. In the 1970, they identified the need of developing a dedicated control facility for the INSAT satellite. The first 4 series of satellites were supplied by Ford Aerospace Corporation. In that study, they identified that such a facility should be established in a place where very near to a place where satellite development would take place. In the year 1976, the frequencies to be used for the satellite for communication was filed with WPC. So it was clear that the C-band and S-band frequencies to be used for the geostationary satellite. Now, the facility the satellite should be a multi-purpose satellite. The control center which is going to be established should coordinate for all the orbit-raising activities and coordinate with all the other centers which are used, or all the network of stations is used for the orbit-raising center. And also it has to be interacted with the user agencies like the meteorological department. Now, when the control center was to establish, there are certain factors to be considered. So in order to locate a control station such that no other country, suppose when you are uplinking an RF frequency, the radio frequency should not interfere with the microwave frequency systems of the other country. So now the particular control center has to be established minimum 500 kilometers away from the nearest country. Now suppose if I look at it, if you go north, you have got the west side you have got Pakistan, north you have got China and Nepal, left you have, the other side you have got Bangladesh, south you have got Sri Lanka. In those days, the nearest RF station was there in Jaffna. So finally, the committee which looked into that, they identified 2 places, namely Hassan in Karnataka and Anandapur in Andhra Pradesh. Finally, the site was Hassan was selected as the best possible site. So Hassan was selected. I'm happy to inform that one of my grandfather's brother was there in the site selection committee. His name was Badrinath, who worked in frequency coordination, and he was an expert in ICC. He was interacting with Vikram Sarabhai and other people. So finally Hassan was selected. Now, just to recall, these are the control center which is going to come in Hassan is used to control all the geostationary or satellites. Basically, when I say a geostationary satellite also takes 24 hours to go around the Earth once. So now Just to recall, there are three laws of planetary motion. The time taken by the planet to go around the sun is called period of revolution. And three Keplerian laws. The mathematician is a German mathematician who formulated three laws. All the planets are moving in elliptical orbits around the sun with the sun in one of the foci. The radius vector, the second law is called law of areas. The radius vector drawn from the sun to the planet sweeps up to equal areas and equal intervals of time. The third law is very, very important to find out the distance at which the satellite has to be positioned in order to make it geostationary. That is, t squared is proportional. That is, if t is the period of revolution of the satellite, and r is the radius vector, and t squared is proportional to a cube. So, using this law, if you keep a satellite at a distance of 36,000 kilometers, the satellite appears to be stationary for an observer standing on the surface of Earth. What is typically the pictorial representation of that. So it is very easy to compute that at a distance of 36,000 if keep only, the satellite also takes 24 hours to go around the Earth once. Now geostationary orbit, now see, Earth is revolving around its own axis. We are sitting on the surface of Earth. Since because of huge mass, we don't feel it. Now for a stationary observer on the standing on the surface, if I look up, if an object appears to be stationary, it's not moving. Such an orbit is called a geostationary orbit. But it is typically a geostationary orbit when whatever you are. Now I have drawn an imaginary line from the satellite to the equator. The point at which the imaginary line drawn from the satellite to the meets the equatorial point, that is called a subsatellite point. The trajectory of the subsatellite point over a day, it follows a figure of 8. Now, then you may ask what are all the other reasons MCF Hassan was selected. Now, geological, for example, when you have established a control facility, the region should be free from the seismic activities. So you have got a strong Deccan plateau, and earthquakes is very, very, very minimal in Hassan, and less susceptibility to floods and earthquakes. And the most important thing is when you have a control center, the tracking capability, you should be able to track majority of it. So maximum visibility in the geostationary arc means from 0 to 150 degrees, whichever satellite you are positioned, you are able to track. The second one is the less interference of the telecommunication installation, radar and corona discharge, and the interference from the terrestrial MIO station. And secondly, and availability of lands and roads, and it should be very near to the ISRO headquarters where the satellite is going to be built. Now, what MCF does? Actually, it coordinates with all. For example, when a satellite is launched, actually, the satellite will not be visible for Hassan all the time. So we take a network of stations across the globe to support the launch. So MCF Hassan coordinates with the network station for the pre-launch activities. The MCF is used to monitor all the INSAT satellites, the GSAT satellites, the navigation satellites for the initial launch and the early orbit phase operations. So once the satellite is launched and positioned at the intended longitude, the payloads which are there on the satellite the performance of the payloads has to be ascertained before declaring for use. So we call it as on-orbit test, where the payloads have been tested in the lab, and once satellite is put in that hard vacuum, we have to assess the performance. So we do what is called in-orbit test of all the transponders before operation of the satellite. And finally, we maintain all the geostationary and the INS satellite, including the spatial operations. Now, this is the site data of Hassan. What is the latitude, longitude, what is the annual rainfall, what is the total campus area in Hassan. So this is what exactly it shows that from Hassan, we are able to track all the satellites starting from 0 to 155 degrees. All the that's because that's what I said, maximum geo arc visibility. Now this is the facilities available. We have got a main campus, we have got a satellite control center, there is a communication, we have got a compute room, there is a data reception, data rack room, we have got the image processing room, and the facilities for the other facilities available for like the diesel generators. There are stations, there are now, as of now it is 7, there are 11 stations actually. And we have got a mission analysis room, there are so many conference halls and so many other facilities. Just to list out the launch. We have got to control all the on-orbit satellite, there is a separate facility. To support the launches, there is a launch control center with all associated hardware, etc. Yeah, typically there are 21 communication satellites, there are 9 navigation satellites, there are 8 satellites which are controlled from Bhopal, Totally 30 satellites are being controlled. So this gives the total number of split up of the number of satellites which are controlled from different longitudes. Totally we have 11 orbital longitudes, where 11 orbital longitudes we are controlling 30 satellites. Maybe in the coming slides, probably you may be seeing that in a particular longitude we are controlling, for example, if you take the 83-degree longitude, there are 6 satellites, and even for 55 also there are 6 satellites. So basically, what happens is, even though you have got the problem is, when you are like we are not, even though we have got 30 satellites, 30 longitudes are not allotted. Depending on the demand, the International Telecommunication Union allocates a certain number of slots for each country. So when you have got a limited slots, you have to control position more than one satellite, depending on being at the frequency and the kind of operation. So controlling and maintaining more than one satellite in the same satellite in the same longitudinal position is called co-location. So we have co-located 6 satellites in 82.06 and in 50.0. So this gives a split up. So this is what it's a pictorial representation of which are the spacecraft which are being controlled in different longitudes and how many satellites are being operated. So this is a very old picture which shows the there is a old picture. There is a change in that computers have been upgraded. These are all the old wax systems. Now it has gone to Linux systems. This is a typical 13-meter antenna used for the tracking. This is the kind of the RF equipments. So this is the corresponding the power complex, the support systems which are used, the diesel generators. So typically we have to get the power. So suppose in case of power loss, we have for all critical facilities, we have the battery backup, where it automatically takes over and provides the equivalent 220 volts facility it can support. So you need some minimum, maybe some few minutes to switch on the diesel generators. So we cannot, so that's why each critical facilities, including the earth station, the control center, is supported by diesel generators, corresponding battery backup, so that there is no power loss, means that there is no signal loss or so types of orbit. A geostationary orbit, the satellite period is same as that of the Earth. Sun synchronous means these are the remote sensing satellites which goes pole to pole. Okay, so typically around 800,000 kilometers. And near microgravity and scientific government, low Earth communication satellites, that are called near Earth satellites. So now, what has happened is, even though the satellite is, for example, a satellite is launched, normally for the initial phase we use full motion antenna. There are 3 kinds actually. What is called a full motion antenna, where tracking capability is there across all the we call it as the 360 degrees. It is called the azimuth. Vertical it is called the elevation. Okay, 92. So MCF. So whenever a satellite is going to be launched, to put the satellite in operation, you need a smaller antenna. Means that even though satellite launches takes place, the infrastructure we cannot bring it up because you have to follow all the governmental procedures. So you need a dedicated antenna. So bigger shows the comparison of time frame. See, for example, in the 2006, this is the where our campus one. It is divided into 4 campuses. So the middle road, whatever it is, you are seeing, it is the road towards the Halebid. Now this is the way the different earth station facilities was there. Now you can see after in 2021 how much the in terms of ground infrastructure and the facilities have grown in terms of the earth stations in different frequency bands, starting from KUDBS, L band, and so this is the Google map. So now over a period of time from 1982 to up to 2022, how the number of satellites have grown over the years. And similarly, the number of antennas in 1982, there when I joined, actually there were only 2 antennas. Today, around 82 antennas are there. So this is a pictorial representation of the equatorial geostationary orbits. Then, for example, see, normally all the geostationary satellites go around the equator. Now, suppose if the orbit get tilted, means it deviates. If suppose it doesn't go around the equator, the angle subtended between the orbit and the equatorial plane is what we call it as inclination. So this is what you are seeing. And similarly, the polar orbits like that. Now, having given the brief introduction of the thing, The life cycle of a geostationary satellite consists of three distinct phases. The launch and the initial phase. The on-orbit phase means that once you launch and position the satellite in the required allocated longitudinal slot, then the life of the baby has begun, and we have to maintain the baby till its end of life and end of life of operation. These are the three phases. See now, when I say launch and early phase operations are very important critical activity in a satellite mission, the launch vehicle actually injects the satellite into a parked orbit, or the GTO, we call it as geosynchronous transfer orbit. In the space shuttle carries satellites into a lower orbit, circular orbit. Similarly, we have got Delta, and similarly we have got the Russian launch vehicle called the Proton, which directly puts the satellite into a geostationary orbit. See now, when a satellite is injected, the nearest point to the Earth is, we call it as a perigee. The farthest point to the Earth is called the apogee. Okay, so now, particularly for the Indian launches, the launch carried out from Sriharikota, after the liftoff, there is a radar called MOTR, multi-object tracking radar at SHARTS, which tracks the trajectory of the launch vehicle. Now, and the ground itself, because the launch activity, the countdown, everything starts few hours before the liftoff. Even the cryogenic propellant is filled to the particular cryogenic engine and tanks few hours before the previous day. Once the cryogenic fuels are loaded, if there is a launch delay, it is very difficult to take out that. So one has to ensure that the weather condition and everything is pakka. Then only the cryogenic fuel is loaded to the rocket. So now, once the countdown or the activity starts, the telemetry transmitter, which is used to send the signals to the ground station, will be kept on before the liftoff itself. So now, once the satellite gets lifted off, the telemetry transmitter is where. So now, after 100 seconds of the liftoff, the launch vehicle trajectory data is actually acquired by the MOTB, that is multi-object tracking radar. It sends the azimuth and elevation tracking angles to the MCF via dedication communication links. Once these angles are acquired, the antenna at Hassan, they track the launch vehicle. So they track the launch vehicle, and finally we get the telemetry signal from the satellite. Now, the advantage is the interesting part is the rocket is moving. Within 100 seconds of liftoff, the telemetry transmitter, which is where the satellite is still inside the rocket, we want to know the first cut health of the satellite. The satellite is the rocket is moving in the predicted trajectory. The telemetry transmitter. Soon after liftoff, we wanted to have the first cut assessment of the spacecraft, which is there inside the rocket. So now, using the CDM, that is computer driven mode, that actually the data comes in a UDP format called user datagram format. The MCF systems they acquire, and finally the signals will get logged. So the telemetry data will come almost for 3 minutes. So data is acquired and logged onto our computers or servers. So we come to know the first cut assessment of the spacecraft still being in the rocket. So this is typical actual how the azimuth and look angles, the tracking angles which you receive from the Sriharikota. Yeah. So now for a launch activity, what is the prerequisites? So normally we configure two earth stations, one prime and backup, with two uplink with two uplinks and two downlink chains. The network stations across the because if there is a failure of a prime station, the alternate chain should be used. And communication with the launch pad and other network, as already told you, because once the launch takes place, for example, for all French Guiana launches, the satellite is visible over Hassan within 90 minutes. Whereas in the case of the Sriharikota launches, Hassan visibility comes only after 24 hours. Only the first visibility comes in the Bayak and other stations across the globe. So we use the network of stations across the globe in order to get the satellite telemetry, so that we should come to know the health of the spacecraft. So mission computer systems are also configured in redundant chain. The power supplies also is configured in the redundant chain. So this is what I was trying to say. We use one station in US called Fillmore. It's an Intelsat station, and then other one is called the Fuchin, which I had gone. So these and finally we have the launch pad. Suppose is the French Guiana, For example, the GSAT-20, which is going to be launched on 18th on Monday, is going to be launched from US using SpaceX Falcon 9 rocket. So this we use a network of stations to track the satellite, and finally we pay for that. Similarly, when suppose if a foreign satellite launch is there, they use our facility. This is the typical network stations. Yeah, this particular diagram explains what are the activities being done. Of course, future slides will give you a detailed explanation. For example, as what already I told you that once the satellite is injected, it is injected to a parking orbit of 300 kilometers by 36,000. Means that apogee is 36,000, perigee is 300 kilometers. So out of the 80% of the fuel, that is oxidized fuel, which is carried out in the spacecraft, will be used to raise the perigee height to geostationary height, that is 36,000 kilometers. So you can see these. So to raise the perigee height, there are certain special, there are heavy engines called liquid apogee motors, which are fired. We call it as the LAM operation. So they are all well-planned activities. It has to be done meticulously. 3 such activities are done. So after 3 such activities, we can see the orbit rising. The orbit of the spacecraft is almost going to the geostationary orbit. Finally, there are appendages which are all in the restored condition. So complex maneuvers has to be done where we have to reorient the satellite and make the satellite to orient the sun and make the deployments of all. You can see the finally deployed configuration. Yeah. So typically now once the satellite is injected, the ideal geostationary orbit is that when I say 42,064 kilometers, Earth radius is added. That is 6378 plus or minus 7 kilometers. So normally the inclination should be 0, means the satellite should go around the equatorial plane. The eccentricity also of the orbit should also be 0. So now what we do, once for example, once this, as I said, the satellite is, for example, for all French Guiana launches, once the launch takes place, the satellite is visible over often after 90 minutes. So in order to track the satellite, what we do, we point 2 antennas to pay a position, what is called the acquisition of signal. Means we have to get the first signal from the satellite. So 2 antennas are positioned. One is kept in an automatic mode. Now, means that the locus of, we know the trajectory how this is going to come based on our flight dynamic software. We preload all the antenna look angles, so it tracks the satellite automatically. The other one is driven in a manual mode. And once the satellite, once the satellite comes after the injection for visibility over Hassan, we track that. The first signal which is received, the signal will get logged. We call it as AOS. So that is indicated by one of the what is called automatic gain control. We get a signal. Okay. So once the satellite is tracked, once the AOS is done, we look at the first cut assessment of the satellite after injection and confirmation of propellant venting, because once the satellite is injected, there should not be any leakage of propellant. And there are certain deployments which has to be done, which has to happen automatically after injection. And to verify the confirmation that the satellite, the commands which are sent from the satellite, we send certain test commands are sent to, so that we are able to communicate with the satellite. So soon after injection of the satellite, the first activity which is done from Hassan is acquiring the first signal, which is called AOS. Next, once the signal is established, we send certain test commands. Then telemetry reception, and also we should also assert time, means that because at simultaneously other than Hassan, some more station may have the visibility. So they track the satellite and send the data. And similarly, in order to know for next few hours, they will not, because till first major orbit rising activity is done, there is no much activity except to know whether we have reached the corresponding intended orbit, in what rate drift it is, what is the initial orbit, and where it is drifting, what is the drift rate. In order to know that, we carry out what is called a ranging operation. We send a signal and receive a signal with a delay using the Doppler effect. We find out, we collect the range data, and using our orbit determination software, we find out the satellite attitude maintenance and solar array sun pointing. And similarly, when the satellite gets injected, the satellite will be still there in a drift mode. So in the process of that, there are already some satellites which are working. Means that there are different satellite operators. So we have a priori, we have to inform all the satellite operators in the world that our satellite is launched. On the way, it may visit you. So in the process, the satellite which are operation, there may be a frequency clash. Means that they will, whatever frequency which is used for uplinking a command, the same frequency may be used by some other satellite operator. So in that process, we have to coordinate with the external satellite agencies, see that the drifting satellite will not interfere. Okay, so that is called the flyby coordination. And similarly, the next is once the satellite is injected, the thermal management is also another important activity. Means that all the subsystems will have the kind of operating temperatures. We have to see that the operating conditions of all the subsystems and all the components, they are well in the well condition. And similarly, when the satellite gets injected, it, at some point of the times the satellite undergoes eclipse, there will not be any generation of power. We have to see that there are onboard batteries which supports the activity. Now, there are, in order to know the drift and the angles, there are gyros are available. So the calibration of gyros has to be done. It has got the temperature dependence. So gyro calibration is done where you have to be precise. Otherwise, the gyro drift will create a lot of problems in making planning their activities. So there are certain reference optical sensors called Earth sensor, the sun sensor, the star sensor. So gyros are calibrated at a stable part of the orbit where the satellite visibility is okay, and also sometimes it happens is some of the objects like sun and moon may come in the field of view of the some of the sensors. So we have to see that the sun and moon doesn't come in the field of view of the some of the optical sensors which is used for satellite operation. So those periods only the gyros are calibrated. Next, the lamp firing, what I told is 80% of the fuel which is used for orbitalizing, we fire at they're all heavy duty engines, which is used for raising the perigee height. And land firing guide is carried out multiple, as I told you, some three burns it is done. And lamp burning is done based on, when you try to plan we call it a liquid approach motor. Okay, so that whenever we want to carry out a lamp activity for the rising of the perigee height, we have to take into account the visibility, the sun moon intrusion of that sensor. When such intrusions are we have to ensure that the satellite is visible over Hassan. Okay, so unless the prime control center, the satellite visible, we don't do any LAM operation. So approximately 80% of the loaded propellant is consumed for the only 20% of the fuel is used for maintaining the satellite throughout its satellite life cycle. Now, once the satellite is placed, LAM maneuvers are we have taken to the right orbit, the stored appendages like the solar panel, solar and the reflectors are deployed, and stored appendages are deployed using pyrocators. And for example, when we want to use deploy certain antennas, the spacecraft is reoriented towards sun heating is done, so that the minimum temperature is required to use the pyrocators. Now, 3-axis stabilization is basically what happens is there are certain actuators which are called momentum, which are nothing but the gyroscope spinning at a specific speed. Now, it gives what happens is because when the satellite is positioned in the orbit, because of the solar radiation pressure, over a period of time there will be unwanted disturbance. It gives a tilt. So, in order to damp out the unwanted disturbances, these actuators they rotate in what we call it as angular momentum, that is bias momentum system. You get a stiffness along the axis. So the switching off all the momentum wheels is done either at the 6 p.m. or 6 a.m. condition. And now these the actuators are commanded to rotate at a particular speed. But what happens is the natural frequency of the speed actually coincides with some of the natural frequencies, some of the optical elements. So we have to ensure that because if these frequencies they match, it leads to interaction, leads to resonance. So we have to ensure that the moving elements like earth sensor, scan mirror, and other things, these interactive zones are avoided. You have got what is called a magnetic torque, so that there are certain oblateness. So the torques are used to correct the earth oblateness effect. Now, final lamp firing, the final liquid oxygen motor firing is carried out almost near to the parking latitude. So now, after the final lamp, when the satellite will get certain drift either in east-west, either it moves towards the parking identified slot with a small eastward drift. And finally, in order to position the satellite, see, for example, it is something like that we are traveling we are traveling from Hassan to Bangalore, say we are come very near to that. Now, once you reach the destination, you have to stop. Similarly, the satellite gets drifted, it's moving towards its intended position with a certain drift rate. So once the satellite comes very near to its intended longitude, we have to stop it. So we have to acquire the satellite or we have to stop it. We do what is called station acquisition maneuvers. They are optical sequence of maneuvers which are called east-west maneuvers using the small pulses. Using there are equivalent, like when I already told you, there is a heavy engine called liquid apogiometer. There are small thrusters which also give which also is similar to which it uses oxidation field and it gives pulses for a very short duration of few milliseconds. So using those thrusters, we use to correct and we call it as a trim maneuver. Means sometimes what happens is when you try to stop the drifting satellite, it may overshoot. So finally, it is something like a simple pendulum. So velocity has to become zero. So we do a optimal set of maneuvers called the trim maneuvers to position the satellite at the intended longitude position. Now, once we position the satellite, the active lifespan of a satellite is typically around 15 years. Now, the satellite is now typically the lifespan of the satellite is generally decided by the amount of propellant available. See, once, for example, suppose if you are able to save some fuel, it means that when a satellite is injected, we give to the our requirement to the launcher, means what is the optimal injecting parameters, means what inclination it should get injected, what is the drift rate, what is the eccentricity, what direction, what is the argument of perigee, what is the rate ascension of ascending load. These are the parameters we give the requirement. So based on our mission requirement, the launcher will tune its launcher and inject the satellite. So now, if you are able to, if you get the optimal injection parameters, we'll be able to save some fuel, which in turn translates into an increase in satellite life. So, however, there are cases. So, the lifespan of the satellite is generally decided by the amount of propellant left out after placing the satellite in the intended longitudinal position. There are many cases where the satellite life gets ended prematurely due to some anomaly in the spacecraft because of propellant leakage or electrical short, you have the bus system short, and you don't have enough power to maintain the systems. Now, once the satellite is positioned in this, the activities done at MCF, which contains health monitoring, the activity maintains the orbit maintenance, the co-location management, as I already told you, placing and maintaining more than one satellite is called co-location, and eclipse management, contingency handling, performance evaluation means you have to once every day you have to assess the performance of all subsystems and remaining propellant estimation, because we should also keep a track of how much propellant so that once the end of life is reached, we have to reorbit that. And similarly, over a period of time, because of the degradation, the properties, solar power also you don't get the sufficient solar power over a period of time. So there is a degradation in solar power. And also we should also look at the space weather monitoring, because the CMEs, whatever the corona mass ejection happens from the sun, have an impact. So sometimes it will knock out the major electronic components. So the space weather monitoring is also an important activity. So now the health monitoring, when I say from the satellite, say whatever we are getting, tele means distance, metry means measurement. So telemetry means the distance measurements, means we are getting the data in the form of analog signal. So that is decoded, and each satellite we got around 2000 parameters coming from the satellite. So the whatever parameter, which telemetry parameter may be a voltage or a current or a status, it could be anything. So real-time health monitoring is carried out using what we call a bundle of software, which is called SCMAC, Satellite Health Monitoring and Control Software. Around 200 softwares or 200 applications are there, which is developed in-house. So SCMAC provides different kinds of alarm monitoring, because when you maintain the satellite, we should also get alerted if there is a deviation. So, or if a particular parameter crosses a limit, we should get an alert, we have to take an action. So there are two kinds of alarms. What is called a limit alarm, which is a soft alarm which generates both visual alarm display on the computer monitor so that it is archived. So we can look at it whether what is the problem and we have to take necessary action. For example, there will be at some point of the orbit, some component temperature may go low. So it gives an alert that the temperature has gone, it has lower limit, we have to switch on the heater. There is which is another what is called a critical monitoring. It generates an alarm with an audio beep. Till you acknowledge it, it will not go on giving over. So when you acknowledge, you get a menu, means for that particular critical alarm, there is a defined procedure. Means that there is a problem in the satellite, you take action. So there is a critical alarm monitoring with visual alert is also there. Now, see what happens is normally because the satellite is visible 24/7, we get every second data. This means within 1.024 seconds, means 1024 milliseconds, we get the same 10 satellite telemetry parameters repeated. But sometimes what happens is, and each means that some parameters they come in parameter in a single word, means octal. Some parameters comes in two different, that means we call it as frames, the 1024 frame. Some parameters may occupy two words. So sometimes what happens is there is a requirement of monitoring the same parameters in the closer look. So there is a feature in the spacecraft what is called the dual telemetry, where we can use this feature and get the same parameter repeated. There are some 10 such parameters we can select. The same satellite parameters can get repeated as a dual channel so that we can have a closer look at it. So normally we do this kind of activity when we do the maneuvers. Okay. Similarly, what happens is some of the parameters we plot it as a function of time, we call real-time graphics. So we look at the, so means what, as the satellite data comes, they get plotted. So we have a software called RTG. So we look at it. By looking at the trend itself, will come to know. Suppose if there is an anomaly in the satellite, it gets reflected in that real-time graphics, where it is graphically plotted in real time. Means every second whatever data gets plotted. So there is certain near real-time monitoring is also available. And PC-based monitoring, what happens is there are certain parameters, like for example, there are certain cameras, so-called the biharial residual radiometer, which is used to take pictures of the Earth. Now in the data satellites, we have what is called the imager and the sounder, where we takes the Earth picture, we give a command to the spacecraft to start scanning that. It takes 30 minutes. So typically in a day, we can take 48 pictures. And these pictures are received by the Indian Met Department. They use these pictures for their weather forecasting. Similarly, in MCF also we have this facility to process, and our group was responsible for the development of the image processing software. But we have this facility to know the payload is working or not. So now what happens is, because of some of the as I said, because of the space weather, there may be suddenly the camera, one of the position may get shifted. So, and there may be certain cases where the Surya, the mirror position may get, so we have to bring back. There are some transponders, we call it as an attenuation. There may be spurious changes. So we use a special software in the PC-based monitoring. Now what is another important activity is we should be able to, like what we are talking, we use a language, we should be able to communicate. So satellite commanding is a routine activity required to carry out the subsystem operation. Means, suppose if you want to change the status of a particular equipment, we want to switch on a heater, we switch on, so we send a tele command. So all planned and time-tamed commands or activities carried out using, see now what happens is, when I send a command, the command is typed, it is called, so we using the command software, we type the command, there will be a hardware called the command encoder. The command will get loaded on the command encoder. Finally, using the high power amplifiers and the antenna, the command will get uplinked to the antenna. So onboard antenna, it receives and goes to the onboard subsystem command receiver. So it is a little bit complex process. So what are all the commands which should be sent to the spacecraft is scheduled through a software called a scheduler. So the satellite controllers, so the schedule is loaded the previous day itself. So at the time of execution of the command will get popped up on the command. So the spacecraft controller, which is sitting in the console, has to look at the read and properly read it, and sometimes they have to look at some other data and transmit the command. So condition-based command means certain, because when you want to send a command, it has to be done looking at certain satellite data, it has condition. So that such kind of activities we call as the operation directives. Now, what happens is, when a satellite in operation, we have eyes. So when because of our eyes, we are able to look at other people. Similarly, on the satellite, there is one particular instrument called the Earth sensor, which is similar to our eyes. The Earth sensor will be always looking towards the Earth. As long as the Earth sensor looking towards the Earth, we call it as satellite is Earth locked. So in order to get the telemetry from the satellite, the Earth sensor should be looking at the Earth, and a signal should, so then only we get the RF signal locked on our receivers. Now because of some perturbations, if the earth sensors gets knocked off, okay, then we lose the signal, we lose the satellite, we call it as loss of link. So now what happens is, on the satellite, we may get some anomalies, some processor may hang up, some actuator may hang up. So some anomaly may happen on the satellite. For certain anomalies, the human beings may not be able to react so fast and needs a faster response. For known anomalies which needs a faster response, and we have to send certain commands which takes the satellite to a space as a safe condition. We define what is called as events. So event is basically a condition based, it's like an expression. We see that, okay, if this particular anomaly happens, you send these commands automatically. There is an event software which is running in the background. It is an intelligent software, similar to an AI based, whatever we call it as. So events will be running in the background. It look at certain conditions, it evaluates the expressions, and if that anomaly happens, without manual intervention, it sends the certain commands to the spacecraft automatically, so that the satellite is safe in the safe condition. So it is more than enough. So for each spacecraft, depending on the type of anomaly, the known anomalies, minimum 10 to 15 such events have been defined. In the latest satellites, we have got certain automated features, like certain heaters can be what is called programmable autocad, PATC, and we can load certain commands on the spacecraft where it gets executed automatically on board, called time tanker command. We got what is called the configurable CCB command. And similarly, there are certain onboard hardware features called fault detection and isolation, FDIR, which is an automated hardware feature. Suppose if there is a processor hung up, it changes to the other processor automatically. So that, and now once that, these are some of the way how we do. Now satellite data analysis is another important activity carried out by subsystem engineers on a day-to-day basis. So you have to evaluate the performance of see that any performance deviation is there. So all the subsystem engineers, they use all statistical and mathematical and graphical tools to evaluate using schematic software, and data is poured into. Sometimes if there is, for example, if you look at a close, you have to, there are tools available where you can get the data ported to the Excel format. And similarly, long-term trend analysis, for example, we are interested in looking at the performance of a particular parameter of the satellite over the years. So trend analysis over the years, and the configuration, and by example, seasonal variation, day-to-day variation, we are able to superimpose data over the years of same parameters. By 5 years data, I can superimpose and see whether there is a deviation, there is a degradation. The other important element which requires continuous monitoring are the mission. So these are the kind of some of the important monitoring, that battery condition performance, battery eclipse performance, degradation of the solar array, that whatever actuators I told, the wheel performance, the thruster performance, temperature rise due to thermooptical property degradation, the gyro rate and propellant pressures. And now the next important activity what we do is the predicting the life estimation. Means because it is very crucial to estimate the life of the satellite, so that once when I say the satellite life it comes to an end, we say that almost the fuel which is carried out is getting depleted. So whenever we do an activity to correct the risk, some amount of propellant is consumed. So for example, if there is a large disturbance, then it gives for a, see, we cannot see the precise estimation of the propellant use is very crucial, because 1 kg of fuel, if you suppose if you deorbit early, it leads to the lot of revenue, because even 1 day life itself gives a lot of revenue. So users need minimum. So for example, if we suppose we are going to, the satellite is going to end, then we have to inform all the users that the satellite is going to land. They have to switch on, they have to switch over to other alternate satellite. So similarly, orbit maintenance, what happens is there are two, briefly tell you. See, for example, because of the satellite orbit is get perturbed by lunisolar gravitational attraction and the solar radiation pressure and the onboard thrusters. Because of the unidirectional lunisolar attraction, satellite orbit gets tilted. Means the orbit, which is the satellite which is revolving around, which is going around the equatorial plane, the orbit will become inclined. So maximum of inclination of 0.1 degrees is allowed. Means normally a satellite has to be maintained within a rectangular control box of point plus or minus 0.1 degrees. Means that suppose if 74 degrees is the control longitude, the satellite can drift 0.1 degree above, 0.1 degree below, and east west also 0.1 degrees. Means that the suppose if you take the center of a rectangle as 74 degrees, we are supposed to maintain the satellite within a control box of 74 plus or minus 0.1 degrees, both east, west, and north, south direction. So this is typically the solar gravitation satellite over the period of time at the different vernaculars and other things. The orbit maintenance was orbit determination using, for example, as I already told you, we do what is called the ranging activity. And so in order, I already told you, because of lunisolar gravitational attraction, the orbit inclination grows over a period of time. Orbit to get 0.1 degrees. Once 0.1 degrees is reached, we have to reposition we have to bring back the 0.1 degrees to zero inclination. Means we have to change the right ascension of the, you have to flip it by, you have to overflip it by 180-degree phase. So we do what is called north-south station keeping maneuvers. And already I told you, because of the Earth oblateness, there will be the Earth oblateness because the Earth is geodal. The gravitational potential on the surface of the Earth varies from place to place. So this variation of gravitational potential on the surface of the Earth is, we call it as triaxiality. The triaxiality induces a unidirectional oscillation aiding in the same direction, because Earth moves from west to east. It adds a acceleration which is called tesseral acceleration. So tesseral acceleration has to be controlled, but what we do is using east-west maneuvers, and also the solar radiations which is impinging on the solar panels over a period of time will bring unnecessarily perturbation on the satellite. The SRP has to be contained. So, and similar, that's why other activities which are done is event prediction, the repositioning maneuvers, and the repositioning and a close approach, particularly in terms of co-located satellites. And ranging is the one operation which is carried out, already I told you, using, we send a signal, we release a signal using a Doppler effect. Finally, we translate it into the linear range, and antenna loop angles are collected. And NSSK is required to correct the orbit inclination. And see, basically a non-zero inclination leads to periodic latitude and longitudinal variation. And basically, already I told you, inclination buildup is due to unidirectional lunisolar, typically up to 0.59 degrees per year. This is the change, and we need a velocity of the correction to vary around 40 meters per second to 50 meters per second. That's the velocity correction we have to do. And similarly, the orbit inclination are corrected by using a thrusters in the north-south direction, or depending on the kind of thrusters, where we change the orbit plane by 180 degrees. And whenever we do, typically 6 times a year we have to do this kind of maneuvers. See, now when we want to do the maneuvers, we have to take it to, because in the coming slide there is one more satellite eclipse comes into picture. Invariably 2 times a year the satellite undergoes the satellite eclipse for a period of 45 days, starting from August 29 to October 14. Similarly, February 29 to April 14. Typically satellite undergoes, there will not be any generation of power. Okay, so that time the satellite is supported by using the batteries, and we have to sustain certain loads. The batteries will get discharged. So we have to ensure that we are not doing any maneuvers during the eclipses, because it takes many hours for the batteries which are discharged to get recharged. So whenever we do a thruster firing, the thruster firing is limited to 175 seconds. The constraint is based on, because whenever you carry out an activity, there will be a sudden rise in temperature which is called a soak-back effect. Okay, because of soak-back temperature, we ensure that the soak-back temperature doesn't reach a higher value. So this is what I was trying to say, that the satellite has to be maintained within what we call the sub-satellite point. Sub-satellite point, already I told you, is when I say that is imaginary line drawn from the spacecraft to the equatorial plane, the point at which the imaginary line cuts the equatorial line, that is the sub-satellite point. The sub-satellite point has to be maintained in a control box of plus or minus 0.1 degrees. So once the inclination change takes place to reaches 0.1 degrees, because of the lunisolar gravitational attraction, we change the orbital plane, we do a maneuver, and so that the inclination correction takes place. So that already I told you. So now the maximum thruster duration is really. Yeah. So in case of co-located satellite, already told you, the maneuver has to be done in a very, very, very planned way. Means that because when I say that, suppose if 6 satellites are co-located in the same satellite longitude, the maneuver for the first satellite has to be done first. The orbit has to be designed precisely. Then once the one particular satellite is the first satellite in that particular chain of satellite orbit maneuver is done, we have to do, after carrying out the first one only, we have to do the second. After carrying out the second only, we have to do the third. So the sequencing of the orbit connection maneuvers has to be done very, very precisely and meticulously. It has to be planned activity. And also we have to ensure that when we do the maneuvers, we have to ensure that the satellite doesn't come closer. We have to maintain an inter-satellite distance of minimum 10 kilometers so that they don't come and collide. So east-west maneuver, set of maneuver is required for the correction of the eccentricity correction, because the eccentricity for ideal geostationary orbit, the eccentricity also should be 0. So over a period of time, because of the triaxiality and other things, eccentricity also change. So we do eccentricity correction maneuvers. And a small correction in a day-to-day activity, you give micropulses by giving chance of few micropulses non-orbit mode, and the drift and eccentricity is also corrected using extent possible using the east-west thrusters, or by using what we call it as where there are actuators, which are as I told you, momentum which gives a stiffness in the yaw direction, in the pitch. The yaw direction will be there, it gives a negative pitch direction it gives. And finally, the repositioning maneuvers. What happens is, we would have applied for a new longitudinal slot. We would have got the slot approved, but we have not positioned the satellite there. Now, once ITU gives the approval or gives the approval for position the satellite, we have to position the satellite within a stipulated time period. But what happens is, for certain reasons, because of the delays in the satellite launch, we may not be able to position this required satellite in the new allocated slot. Now you have to position you have to secure your longitude. Otherwise, if you don't position the satellite in the required latitude, some other country the ITU may allocate that particular longitude slot to some other country. So in order, in such cases, what we do, the certain satellites which are life is going to end, we introduce a small drift rate so that we move the working satellite from current landing position to the to a position where we are not able to position, so that we reposition the satellite so that the satellite rates are the longitudinal rates are maintained. So the reposition maneuvers involves introducing a small east-west drift rate by imparting a delta velocity and arresting at the target longitude. Depending on whether it is you have to move eastward or westward, the corresponding drift is given. We give a small introduced delta velocity, and after completion of now, what we call it as reorbiting. Now, what happens? You may be wondering that the satellite is positioned in geostationary orbit of 42,000 kilometers, 36,000 kilometers. Now, as I said, the active lifespan of the satellite is around 15 years. Now, once the satellite life is going to coming to end, means that the fuel carried out in the satellite is almost becoming minimum. Then we have to reposition the satellite, means we have to move the satellite from the current orbitation position to a orbit called supersynchronous orbit, which is also called as the graveyard orbit, which is 300 kilometers away from the geosynchronous satellite. It's a measure to show that. So this is what we call it the IADC guidelines. The IADC, there is an International Debris Management Committee. They have given the guidelines, means that once the satellite's life is going to end, we have to reposition the satellite from the current position. We have to raise the orbit by 300 kilometers and position into an orbit which is called a supersynchronous orbit. And it is also called a graveyard orbit. So once we position the satellite, the particular satellite is like a dead body, it will be revolving around the Earth. So now geocentric orbit, the graveyard orbit is few hundred kilometers above the Earth's orbit. Now, in order to position the satellite into their orbit, that's what I said, the precise estimation of the on-orbit propellant which is there is very, very important, because each one day life translates into revenue. So according to IAD's Interagency Space Debris Coordination Committee, is called IAD's again. This is a typical formula, that is 235 kilometers, 1000 CR, where CR is the solar radiation pressure coefficient, and typically air by is the area by mass ratio of the satellite, total area followed by mass. So typically it comes to around 300 kilometers, depending on that. So now, once you position the satellite, once you deorbit the satellite to the graveyard orbit, it has to be passivated. Means that the passivation activity involves removing all the stored energy in the satellite by reducing the probability of satellite integration so that it doesn't explode. Means that the batteries has to be disconnected, all the revolving, the rotating parts has to be, or the velocity has to bring on, and the transmit has to be switched off. So switching off all the rotating elements, momenting element, disabling the battery discharging, complete discharge of battery, and if any propellant is there, you fire the thrusters so that the propellant tanks are depleted, and draining of any other reasons so that the satellite doesn't explode. And finally, we switch off the transmitter so that the satellite life comes to an end. Now, space debris. Space debris is also an orbit debris. The space junk is basically a collection of objects in the orbit around the Earth. They are created by humans, which no longer serve any useful purpose. So these objects may consist of any space spin trackage, defunct satellite, explosion, or collision. So debris monitoring, cataloging is very important activity. See, currently MCF doesn't have the capability to monitor. That's what I was telling the SPROC, when I say satellite photometry, laser ranging, and optical communication. So we are establishing two optical telescope, which is yet to be commissioned, what already I mentioned. So for a time, in order to establish this facility, we were using on a requirement basis the use of optical observatory at the Indian Institute of Astrophysics. At Hanley, our team used, the control center is there in Hoskote. So ISRO is, that's what we are establishing. So as in case by case, we have used the Hanley telescope to find out the sizing of the optical telescope. So satellite, now next comes, I was just already telling, the satellite experience eclipse when the sun rays are blocked by any essential body, Earth and Moon, causing the shadow freeze. So eclipse is due to Earth shadow falling off, and it occurs twice a year. That's what I told you. That is 45 days from August 29th to October 14th, and February to April is the peak. Now initially it starts with an penumbra, and then followed by umbra. It is actually a bell-shaped because it's purely a Gaussian distribution. For maximum 72 minutes it comes. So lunar shadow is actually can happen any day of the year. Lunar eclipse occurs on a new moon day when the declination difference between the sun and moon less than 0.5 degrees. So the occurrence of the umbra is very rare. The worst case penumbra duration is around 350 minutes. We switch off certain loads. So this is a typical geometry, which where at 7.7 degrees, we get the total Earth view is around 70.4 degrees. This is the sun's declination over different seasons. So now I'll just touch upon the navigation satellite. It is a 7 satellite constellation. It is the Indian GPS. So typically some of them are in the geostation. Some have got the GSO with an inclined orbit. The first slide, now at any instant of time 4 satellites will be given. It gives a position accuracy of around up to 20 meters. Restricted will be around 10 meters. It gives a timing accuracy of around 20 nanoseconds. And typically the frequency is used in this 6.4, and then in C-band ranging, and finally we got a CDM ranging, and ranging is carried out for the calibration of the atomic clock, and CCDS protocol and encryption used in the orbit. And it's typically the pictorial representation of the geostation, navigation satellites, and this is typically the coverage area. We got a CDM frequency band, how it is being done. And similarly, now there is this quite important activity. See, that the satellite bus command means that the commands related to the spacecraft systems are controlled from Hassan, which is called. Now there is both Hassan and Bufa. Now whatever the grid correction or the position correction, there is a navigation control is there at Bailalu, that is in Bangalore. Other one is there at Lucknow. So these control centers, they generate the commands, the navigation commands every 5 minutes. These commands comes to Hassan or dedicated links. They come, they get uplinked to the satellite automatically every 5 minutes. So you have got navigation and the grid correction commands, or atmospheric correction commands generated from the navigation control center, which is located at ISRO at Bailalu. The other one is at Lucknow. And during the remaining period, we have to send the satellite bus commands. Okay, there are these we have got CDM ranging station at 4 places at Hassan, Bhopal, Jodhpur, and Shillong, and laser ranging station. There are writing orbit retention states. So this is typically the control facility of that. And finally, interference monitoring. See, for example, what happens is when we delegate the satellite for use, there may be some unwanted users may interfere with us. So we have a facility. So we have to monitor adjacent satellite operating in both C, extended C, and KU bands. Address, suppose if somebody is uplinking without our permission, we have to find out who is the culprit who is doing infringing into our satellite. We also monitor the different transponders of the satellite and verify the communication traffic as a plan. And suppose if some user is overshooting, we also identify non-authorized users. We also predict overdrive. Means that particular uplink power only has to be, there is a restricted power for uplink. So anybody is overdriving, and suppose if somebody is interfering, Ananda, it also we also characterize the frequency and time of modulation domain. So this completes my presentation.
Oh, thank you very much. Very extensive presentation. So many technical things that we could not follow down, obviously.
Because too many slides were there, I just wanted to moderate time for 1 hour 10 minutes.
No problem, no issue.
That is the reason I have tried to give what we do and what. It was little bit, some portions are a little bit heavy, but
a lot of technical things. Yes.
the basic concept what I'm saying.
Okay. Let's see if there are any questions about your talk. Anybody who wants to ask a question, you can raise your hand or ask. To start with, I have a question. How many satellites can you monitor at the same time from MCF? How many they really monitor?
We are monitoring all the 30 satellites.
137?
No, 30. We have 30 satellites.
Oh, 30 you can monitor.
Both us and people, we have the surface configured because each satellite we have got a specific question. You see, what happens is when we launch a satellite, the software which is used to will have a different version. But the schematics, what I call satellite health monitoring, is a suite. It is a common software which is applicable for all satellites. So initially for the launch, you may have changes with respect to depending on the satellite configuration and new version of software. So that software is a separate server is used. Finally, the same software is used for monitoring all the satellites.
Okay. What about the software and hardware components? How much of it is indigenous? How much is imported? Have some idea?
Imported in the sense that the servers are almost imported. You don't get it because you have got the switches which are network switches. It is a Cisco proprietary. It has certain kind of servers. They're all proprietary. But now in these days, lot of restrictions are there for a proprietary item. You have to justify. Suppose if nobody else in the world is supplying. So for example, there are certain amplifiers called high power amplifiers, which there are only 1 or 2 parties in the world who manufacture that high power amplifiers. Particularly US called Varian. They call Gen 1, Gen 2 suppliers. Similarly, particularly antenna feeds, for different frequency bands, there are only few suppliers in the world. Because and demand is not much. These are all very high-tech area. So based on your requirement only they manufacture. They don't make it ready. It's quite expensive also. It turns into few crores. So depending on so that such nothing is available off shelf.
Off-shelf, yes.
Now to place the order, so the deployment or the delivery time may take 3 to 6 months. Okay. So because and for example, from satellite to satellite, your configuration also mentioned your earth station infrastructure, the frequency band, the feed, the size, the type of amplifiers used, they may differ.
Okay. So one more question. You talked about graveyard orbit for satellites which are not working. Why don't you get rid of that? There will be a lot of debris, space debris there. There may be damages. Why can't they be gotten rid of?
That is true. But when you talk about it, 36,000 kilometers over, it is very, very huge area. It's not that too populated. So but whereas the Leo constellations where for example, Elon Musk Starlink, he is trying to give a broadband connectivity to all the rural areas, placing a cluster of satellites, around 4,000 satellites around in 600 kilometers orbit. Each satellite is around 250 kgs. Okay, so that will become in a lower orbit, like 600 to 7, it will become depopulated. And they are planning to increase up to 10,000 satellites. So now, based on your demand, each satellite will get routed automatically, giving a throughput of around 150 Gbps. That is the kind of connectivity Starlink is having.
So finally, how do you want to take care of this debris? Space debris is there. You want to just leave it there or get rid of it or bring it back to Earth?
No, no. In the sense that is why I told the ADC guidelines have come. Probably 10, 15 years back, maybe 20 years back from now, each country wanted to use the satellite to control till last gram of fuel is present. Each gram of fuel translates into your revenue. Now, the ADC guidelines has been very, very clearly told that you have to position the deorbited satellite minimum 300 kilometers above the Earth's surface. Sorry, beyond the synchronous orbit. Now, because the awareness have come, people at least now 6 months life will go. That much minimum fuel is required to raise the satellite orbit to existing geostationary satellite to super synchronous orbit. So 6 months revenue one has to forego. That awareness has come. There is a strict guidelines. Earlier they were not following. Now they are following. Some discipline is there. But I don't say that once you position the satellite in the orbit, nothing else with it. It is like any other dead body revolving. It will not come back. It will be revolving.
Okay, any other questions?
Sir, I have.
Sir, once, okay.
Sir,
In continuation of what Dr. Kagli asked, sir, I want to see clarification. You said that you're running 30 satellites from MCF. Is it the maximum number or only 30 or still capacity is there?
Number. At present, we have controlling 30 satellite, live satellites. Some satellites we have already decommissioned.
No, you have the capacity to handle only 30 satellites.
We have the capacity to even leave up to 100 also. No issue. The question is now, suppose if we are going to launch, we have a plan of what is my vision, what we call a roadmap, means next few years. How many satellites are going to be launched? That's a well planned plan. And where is time schedule of the realization? Now, for a given satellite, if there is a need to improve the infrastructure, corresponding infrastructure in terms of antenna, the ground hardware, the procurement of computer servers, the facilities also will get upgraded. So what is need is, suppose if you want to control more satellites, the corresponding ground infrastructure also has to be augmented.
Okay, we move on to next question, please. So Malaysia wants to ask the question, please. Yeah, for Malaysia, okay. Please go on.
Thank you, sir. Sir, there are two questions. My first one is with geostationary satellite distance, every country has to put the satellite there itself. Is it the crowding of satellite a problem from the point of view of number or from the point of view of the signal?
No, crowding no, for example, that's what I said. No, even though if you have got 30 satellites, the telecommunication, that is ITU, doesn't give you 30 slots to you. They have restricted the number of slots to each country, depending on your need and your program. Not that crowded. And similarly, for example, if you want to position some foreign operator want to position their satellites on Indian subcontinent, they have to take the permission.
Okay, sir. My second question is, you said there is some fuel is needed for a satellite there. Did I get something like that?
Where?
Fuel
Fuel is needed.
Fuel, the fuel satellites.
Satellite fuel like oxidized and nitrogen tetroxide and MMH, monomethyl hydrazine, it is used. So it is called combination of that. So you have got both oxidizer and fuel. See, when you want to reposition the satellite, minimum from 6 months fuel is required.
Okay, next question.
Sir, one more question is that.
Okay, carry.
Sir, regarding the debris only, graveyard, see you are discharging the batteries and all that, and their own maneuvering also will not be there.
Yeah.
So then will they not deviate from their path and collide with others, or how long it will rotate go around the earth? in the graveyard?
I already mentioned, sir, that is before switching off the telemetry transmitter, where we are getting the signals on the ground station, we have to remove all the energy resources, means that we disconnect the battery, we drain the propellants, all the rotating elements, we bring the speed to 0. Finally, we switch off the transmitter. So satellite doesn't explode. However, once you do this, like a dead body, it will be rotating, it will be there only, it will not come back. But because there is no air drag, it's pure hard vacuum. No? Suppose if it is within 300 kilometers over a period of time, orbit will get, finally it may fall on the surface of Earth, like Skylab, other things. Here there is no air drag at all. It's a vacuum.
Next question, Professor Raghavendran.
Yeah, sir, I have one observation with a question and one question. First, I'll ask the question. You mentioned about the Starlink, this SpaceX company's thing. They say that satellites are replacing basically the cell towers. And particularly for remote areas, this seems to be a good solution. Do you think this will be the future of telecommunication? All our cell towers will be replaced by such satellite systems?
Question is that there is a question, economy comes into the picture. Two things you have to address. Whether you want to give a service where you cannot lay optical cables, particularly in the northeast, say. You cannot give the signals. Such places where you are not able to give the good broadband connectivity, probably this is the solution.
Okay.
But economically, you may not get the revenue.
Okay.
Not economically not viable, but you are giving a service.
Yeah.
Okay, next question.
Thank you. And the second part is this. See, after listening to a lecture, it was an extremely well presented one. I feel very extremely proud that our Indian engineers have, developed this state-of-the-art facility. It's an inspiring story. Students must be exposed to this. My question is this MCF facility open to the public schools and colleges? Can we take our students there? And whom we should contact?
Yes, what you have to do, sir? So whoever school or college, they have to write a letter to directly MCF saying that this is the number of this many, probably 1 month before that, listing of the number of students, who is the teacher accompanying, which day you want, which time you want. You have to send a mail or you have to write a letter. Depending on the activity, if too many requests are there, they restrict. They give a reply saying that, okay, in this particular day, you please come. They allocate the particular, the engineer and staff to accompany you and show the facility. So it is possible.
Thank you.
Okay. Next question.
I can give the director's mail address, you can send it. Sending the list of people and the teacher accompaniment, which day you want and what time you will be reaching, and they reply back. So once your visit is confirmed, definitely you can plan a visit there. Once you visit to Hassan, you plan a visit to Belur, Halebid also, because our office is 26 kilometers from Halebid.
Correct.
Back. It can be.
Thank you, sir. Yeah.
Okay. Any other questions?
Sir, I have one question. Jayappa from Marine Geology Department.
Okay. Carry.
Sir, regarding the 30 satellites Anand sir was mentioning, so I want to know the lifespan of those satellites.
I told you in the beginning, it depends on typically how much, suppose the heavier the satellites, more propellant you can carry. Okay, so it depends on how much fuel you would have carried. Heavier the satellite, here is the propellant tank. 20 life. But typically the Indian satellites which are there on in orbit, they have got lifespan of around 15 years. Nominal, assuming that there is no anomaly happening in the spacecraft.
Okay.
But if there is an anomaly, because of the some bug system file, there is no power generation is not there, and the satellite got lost because of something else. Mission closure may be there. But however, if everything goes well, the 50. Design and the weight of the satellite, whether it is a 4K, 4000K satellite, 5-ton satellite, 6-ton satellite, or 3-ton satellite.
Okay. Thank you, sir. Thank you.
Some Indian navigation satellites ಬರ್ತಾ ಇದೆ ಅಂತ ಕೇಳಿದ್ವಿ ನ್ಯೂಸ್ ಅಲ್ಲಿ. ಯಾವಾಗ ಬರುತ್ತೆ? When we can expect the navigation network of navigation satellites?
That's what I told IRNSS.
ಆಪರೇಟ್ ಆಗ್ತಿದೆಯಾ?
I told you 7 satellites.
ಈಗ ವರ್ಕ್ ಆಗ್ತಾ ಇದಾವ?
ತೋರಿಸಿದ್ನಲ್ಲ, already 9 satellites are in orbit. Minimum be visible at any instant of time.
ನಾವು ಯೂಸ್ ಮಾಡ್ಬೋದಾ? We can log on to it and use it for our navigation.
ರಿಸೀವರ್ ಬೇಕು, ಹ್ಯಾಂಡೆಲ್ಡ್ ರಿಸೀವರ್ ಲೆವೆಲ್ಗೆ ಇದು ಬಂದಿಲ್ಲ. ಯು ನೀಡ್ ಸ್ವಲ್ಪ ಪೋರ್ಟಬಲ್ ಲೆವೆಲ್ಗೆ ಇನ್ನೂ ಬಂದಿಲ್ಲ.
ಬಂದಿಲ್ಲ. ಓಕೆ, ಥ್ಯಾಂಕ್ ಯು. ಎನಿ ಕ್ವೆಶ್ಚನ್ಸ್?
ಸರ್, ನಂದು ಇನ್ನೊಂದೆರಡು ಕ್ವಶನ್ಸ್ ಇದೆ.
ಕೇಳಿ. ಶಾರ್ಟ್ ಕ್ವಶನ್, ಶಾರ್ಟ್ ಆನ್ಸರ್ಸ್ ಪ್ಲೀಸ್.
ಸರ್, ಪ್ರೊಫೆಸರ್ ಆನಂದ್ ಬಹಳ ಚೆನ್ನಾಗಿ ಕೊಟ್ರಿ, ಆದ್ರೆ ನೆಕ್ಸ್ಟ್ ಟೈಮ್ ಒಂಚೂರು ಸ್ವಲ್ಪ ಸ್ಪೀಡ್ ಕಡಿಮೆ ಮಾಡಿ ಸರ್, ಒಂಚೂರು.
ನನಗೆ 1 hour ಟೈಮ್ ಕೊಟ್ಟಿದ್ದಾರೆ.
ಹೌದೌದು, ಬಟ್ ತುಂಬಾ ಚೆನ್ನಾಗಿ ಹೇಳ್ತಾ ಇದ್ದೀರಿ, ಅದಕ್ಕೆ ನಾನು ಅನ್ನೋದು ಎಲ್ಲ ವಿವರವಾಗಿ ತಿಳಿಯೋದಕ್ಕೆ ಸ್ವಲ್ಪ ಕಡಿಮೆ ಮಾಡಿ ಅಂತ. ನನ್ನ ಕ್ವಶನ್ ಒಂದೆರಡು. ಇದು ಪೋಲಾರ್ ಸ್ಯಾಟಲೈಟ್ಸ್ ಮತ್ತು ಇನ್ಕ್ಲಿನೇಷನ್ ಸ್ಯಾಟಲೈಟ್ಸ್ ಇವೆಯಲ್ಲ, ಅವನ್ನು ಜಿಯೋ ಸ್ಟೇಷನರಿ ಡಿಸ್ಟೆನ್ಸ್ ಅಲ್ಲಿ ಇಡ್ತಾರೇನೋ ಅಥವಾ ಇಲ್ವಾ?
ಪೋಲಾರ್ ಸ್ಯಾಟಲೈಟ್ಸ್ ವಿತಿನ್ 900 ಕಿಲೋಮೀಟರ್ಸ್ ಪೋಲ್ ಟು ಪೋಲ್ ಸುತ್ತುತ್ತೆ ಸರ್. ಅದು ಪೋಲಾರ್ ಸ್ಯಾಟಲೈಟ್ ಅಂತ ಹೇಳಿದ್ರೆ ದ ಸ್ಯಾಟಲೈಟ್ ಗೋಸ್ ಅರೌಂಡ್ ದ ಪೋಲ್ ಟು ಪೋಲ್, ವೆರಸ್ ಜಿಯೋ ಸ್ಟೇಷನ್ ಸ್ಯಾಟಲೈಟ್ ದೇ ಗೋ ಅರೌಂಡ್ ಇಕ್ವಿಟೋರಿಯಲ್ ಪ್ಲೇನ್. ಇಕ್ವಿಟೋರಿಯಲ್ ಪ್ಲೇನ್ ಅಲ್ಲೇ ಸುತ್ತಾ ಇರುತ್ತೆ. ಆರ್ಬಿಟ್ ಟು ಇಕ್ವಿಟೋರಿಯಲ್ ಪ್ಲೇನಿಂಗ್ ಇಂದ ಸ್ವಲ್ಪ ಇನ್ಕ್ಲೈನ್ಡ್ ಆದ್ರೆ ಆಂಗಲ್ ವಿ ಕಾಲ್ ಇಟ್ ಆಸ್ ಇನ್ಕ್ಲಿನೇಷನ್. ಈಗ ಸರ್
ಓಕೆ, ನೆಕ್ಸ್ಟ್ ಕ್ವೆಶ್ಚನ್ ಸರ್.
ಫಿಗರ್ ಆಫ್ ಏಟ್ ಬರುತ್ತೆ ಅಂದ್ರೆ ದಯಮಾಡಿ
ಫಿಗರ್ ಆಫ್ ಏಟ್ ಏನು?
ಫಿಗರ್ ಆಫ್ ಏಟ್ ಯಾಕೆ ಬರುತ್ತೆ ಒಂಚೂರು? ಈವನ್ ಸೂರ್ಯ ಉದಯವಾಗೋದು ಕೂಡ ಒಂದು ವರ್ಷದವರೆಗೆ ಕಾದ್ರೆ ಫಿಗರ್ ಆಫ್ ಏಟ್ ಬರುತ್ತೆ ಅಂತಾರಲ್ಲ, ಅದೇ ಕಾರಣ ಏನು?
ಹೇಳಿದ್ನಲ್ಲ ಸರ್, ಇವಾಗ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ಈಚ್ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ ಇವಾಗ ನಿಮ್ಗೆ ಸಬ್ ಸ್ಯಾಟಲೈಟ್ ಪಾಯಿಂಟ್ ಏನಂತ ಹೇಳಿದೆ, an imaginary line drawn from the satellite to the equatorial plane. ಅದು ಯಾವ ಪಾಯಿಂಟ್ ಅಲ್ಲಿ equatorial plane ಟಚ್ ಆಗುತ್ತೋ ಆ ಪಾಯಿಂಟ್ ಸಬ್ ಸ್ಯಾಟಲೈಟ್ ಪಾಯಿಂಟ್ ಅಂತ ಹೇಳ್ತೀವಿ. You go on plotting over a day of over 24 hours, you find out the position of the intersection. ಅದನ್ನ 24 hours plot ಅದ, it comes in the form of figure of 8 ಅಂತ ಹೇಳಿ. Locus of sub-satellite point over 24 hours will be formed in the form of figure of 8.
ಥ್ಯಾಂಕ್ ಯು ಸರ್.
ಓಕೆ, ನಂದೊಂದು ಸಜೆಷನ್ ಇದೆ. ಈ ಪ್ರೊಫೆಸರ್ ಮಲ್ಲೇಶ್ ಒಂದು ಸಜೆಷನ್ ಕೊಟ್ಟರು, ಇನ್ನು ಸ್ವಲ್ಪ ಪಿಕ್ಚರ್ಸ್ ತೋರಿಸಿದ್ರೆ ಎಫೆಕ್ಟಿವ್ ಆಗಿರುತ್ತೆ, ಮೋರ್ ಅಟ್ರಾಕ್ಟಿವ್ ಆಗಿರುತ್ತೆ. ಫೋಟೋಗ್ರಾಫ್ಸ್, ಪಿಕ್ಚರ್ಸ್, ಡಯಾಗ್ರಾಮ್ಸ್
ಇದೆ ನಮ್ದು ಅಲ್ಲಲ್ಲ
ಸೆಕ್ಯೂರಿಟಿನಾ?
ಫಸ್ಟ್ ಆಫ್ ಆಲ್ ಇದರಲ್ಲಿ ಕೆಲವು ವಿಷಯ ತುಂಬಾ ಸೆನ್ಸಿಟಿವ್ ವಿಷಯ ಹೇಳುವಂಗಿಲ್ಲ, ನಿಮಗೆ ತೋರಿಸಿದ್ದೀನಿ ನಾನು. ನಾಟ್ ಸಪೋಸ್ ಟು ಟೆಲ್ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಪರ್ಮಿಷನ್.
Photographs of satellites, orbits, and also people working, trying to monitor the radars. It's up to you.
ಸೆನ್ಸಿಟಿವ್ ಆದ್ರಿಂದ ನಮ್ಮ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ನಾಳೆ
ಸರಿ.
ಸೊ ಹಾಗಾಗಿ ಸೆನ್ಸಿಟಿವ್ ಇನ್ಫಾರ್ಮೇಶನ್ ನಿಮಗೆ ತೋರಿಸಿದ್ದೀನಿ. ರಿಪ್ರೆಸೆಂಟೇಟಿವ್ ಕಂಟ್ರೋಲ್ ಸೆಂಟರ್ ತೋರಿಸಿದೆ, ಒಂದು ಅರ್ತ್ ಸ್ಟೇಷನ್ ಫೆಸಿಲಿಟಿ ತೋರಿಸಿದೆ, ಇನ್ನೊಂದು ಪವರ್ ಕಾಂಪ್ಲೆಕ್ಸ್ ತೋರಿಸಿದೆ.
ಓಕೆ, ನಾಗರಾಜ್, ಯು ವಾಂಟ್ ಟು ಆಸ್ಕ್ ಕ್ವೆಶ್ಚನ್? ನಾಗರಾಜ್
ಸರ್, ಕೇಳಿಸ್ತಾ ಇದೆಯಾ ನಾನು ಹೇಳೋದು?
ಕೇಳ್ತಾ ಇದೆ, ಕೇಳಿ.
ಏನೋ ಸ್ವಲ್ಪ ಸಿಸ್ಟಮ್ ಪ್ರಾಬ್ಲಮ್ ಇದೆ, ಅದಕ್ಕೆ ಕೇಳ್ತಾ ಇದ್ದೀನಿ ಸರ್. ಇನ್ನೊಂದು ಒಂದೊಂದು ಸ್ಮಾಲ್ ಕ್ಲಾರಿಫಿಕೇಶನ್, ಸ್ಪೇಸ್ ಟ್ರಾವೆಲ್ ಸ್ಯಾಟಲೈಟ್ಸ್ಗೂ, ಸ್ಯಾಟಲೈಟ್ಸ್ ಅಂತ ಕರಿತೀವೋ ಅಥವಾ ಸ್ಪೇಸ್ ಟ್ರಾವೆಲ್ ಅಂತ ಹೇಳ್ತೀವಲ್ಲ ಅದಕ್ಕೂ, ಮತ್ತೆ ಪೋಲಾರ್ ಆರ್ಬಿಟ್ ಸ್ಯಾಟಲೈಟ್ಸ್ಗೂ ಏನು ಕ್ಲಾಶ್ ಆಗಲ್ವಾ ಅಂತ ನನ್ನ ಡೌಟ್.
ಪೋಲಾರ್ ಆರ್ಬಿಟ್ ಸ್ಯಾಟಲೈಟ್ಸ್ ಎಲ್ಲ ಆಕ್ಚುಲಿ ರಿಮೋಟ್ ಸೆನ್ಸಿಂಗ್ ಸ್ಯಾಟಲೈಟ್ಸ್. ಅದು ರಿಮೋಟ್ ಸೆನ್ಸಿಂಗ್. ಈ ಸ್ಪೇಸ್ ಟ್ರಾವೆಲ್ ಸ್ಯಾಟಲೈಟ್ಸ್ ಇಟ್ ಇಸ್ ಲೈಕ್ ಎ ಸ್ಪೇಸ್, ಲೈಕ್ ನಮ್ಮ ಗಗನಯಾನ್ ಪ್ರಾಜೆಕ್ಟ್